So, we continue with our discussion on analog to digital conversion in this present lecture. So, this is the part 2 of our lecture on AD converter. Let us look at some of the general characteristics first. There is something called resolution we want to talk about for an AD converter first. Now, just like for a DA converter, when we gave a digital input and obtained the analog output, we said that the step height was a measure of the resolution. So, here also what is the minimum change in the input voltage that will result in one step jump in the output, because here the output is digital. So, you see here our input is analog voltage V A, but our output will be digital. Digital means there will be some voltage levels or digital levels. So, the output cannot be continuously changing, they will be discrete. So, as you change your inputs continuously, your output will be changing in steps. Like this. Okay. The resolution tells you that what this is your one step height and what is the input voltage that corresponds to that change. So, you see if A is your full scale voltage of the AD converter, then full scale voltage divided by the total number of steps, A divided by 2 to the power n. This is defined as the resolution. Let us take an example. Suppose I have an 8-bit AD converter with a full scale voltage of 1 volt, then full scale voltage 1 divided by 2 to the power 8, okay, this many volts, this comes to 3.9 millivolts. And so, this if you multiply by 100, you get it as a percentage, right. This is what your resolution talks about. Then comes the dynamic range. So, what is the dynamic range of an AD converter? Suppose you see I have designed an AD converter for some signal, right. So, input there is an analog signal which is coming. So, I know that what is the minimum voltage level and the maximum voltage level in my analog signal. So, I am designing my AD converter accordingly. So, the minimum and the maximum amplitude to be measured, that means input, the ratio between the two defines the dynamic range. Now, there are a few things, let me tell you. So, for a linear AD converter means the output and input are proportional, that is a linear AD converter. The dynamic range can be calculated by the number of bits, like for an 8-bit AD converter we will be having a dynamic range of 256, because there are 256 steps. So, when you divide the maximum voltage by the minimum voltage, that will be equal to 256, right. This you can calculate for a linear converter if it is proportional. But for some application where the input is very large, then you need to just add some nonlinearity to the AD converter, but we are ignoring that for the time being. Just mentioning that for large dynamic range some nonlinearity may be introduced. Now, some terms that we use, resolution of 8 bits, like this we mentioned earlier, and dynamic range, n bit dynamic range. Let us take an example. Suppose we talk about 8 bit resolution and a 12 bit dynamic range. Well, 8 bit resolution means what? To just 8 bit resolution we just now talked about earlier, 1 by 2 to the power 8, which comes to 0.39% if you multiply it by 100, right, resolution of 0.39%. And 12 bit dynamic range means how many steps? 2 to the power 12 means 4000 something, 4096, so approximately 4000. So, range is 1 to 4000. So, it means when you combine resolution with dynamic range, it means that you specify a range, that I want to measure a range of 1 to 4096 with an accuracy or resolution of 0.39%. Both are important. One says that what is the limit you are measuring with, and other one says what is the accuracy with which you are measuring it. Okay. Dynamic range and resolution, both are important in that respect. Okay. Conversion time and bandwidth. Conversion time says that suppose I have an AD converter, right. So, it depends on the design of my AD converter how fast it can convert. So, suppose I am applying an analog voltage V A, in the output I am getting a digital word D. So, how fast it can convert? It can take a time delta. Now, depending on the technology using which you are building this, the conversion time can be a few nanoseconds, it can also be as low as a few milliseconds, right. Secondly, as I said earlier, you will be using the sample and hold circuit in the input, that will determine the input bandwidth, that what is the maximum rate with which you can apply the inputs, right. The conversion frequency will depend on that. So, these are some of the parameters of an AD converter. So, I am not going into the much detail of this. Fine. Let us talk about ADC transfer characteristics. For analog to digital converter, I said that on the input side you have your input voltage, and the output you are getting a digital word. So, it will ideally it will be a step. Now, there can be possible errors. Now, the first error is an offset error. Offset error I already mentioned earlier with respect to DA converter is very similar, that instead of this straight line, the curve is either getting shifted up or shifted down. There is a steady offset, a positive offset or a negative offset. There can be an offset error. Now, why this offset error means occurs, it depends on the actual technology with which you are building it. Okay. Fine. Then comes the linearity or non-linearity. Linearity means, you see, the step heights again quite similar to DA converter, step heights should be equal, but in this case you may find that for some of the steps the heights may be unequal, which means, you see, the steps when you show like this, suppose I have these steps. So, if you join the middle point of these steps, it will be like a straight line. So, the ideal case will be a straight line as this blue line shows. Now, because of this nonlinear error, if you join the middle points, it may show like a curve as this red line shows. This shows the nonlinearity error, right. So, this kind of nonlinearity error can be there, and there can be a differential nonlinearity. This is another kind of error. Differential nonlinearity says that again the least significant value should be constant with respect to the output voltage, but it is not. But for a real AD converter, for an acceptable AD converter, the difference from the ideal value should not exceed half of the LSB value. Now, typically how do I check? We apply a large number of random inputs covering the whole range. Now, the frequency histogram should be equal across all values, but what we will see if there is a differential nonlinearity, that it will not be the same, because ideal frequency should be flat like this black one shows, but for differential nonlinearity you will see that it may vary. Okay. But these are some of the errors related to AD converter. You need not have to worry too much about these things now. Just remember that this kind of errors can take place. Now, let us come to the design of the different types of AD converters. This is more interesting. The first kind of AD converter design we talk about is something called a flash type AD converter. Now, let me tell you, flash type AD converter is the fastest type of AD converter that is known, but the problem is that it requires too much hardware. Let us see how. Flash type AD converter, as I said, it provides the fastest conversion, but it requires large amount of hardware. In what way? Suppose I have an n bit AD converter, I need 2 to the power n minus 1 comparators, 2 to the power n resistances and one priority encoder of length 2 to the power n. Let us talk a little bit about this. Well, we talked about a comparator here, right. So, what is a comparator? This is not a digital comparator. Here what we are talking about is something of an analog comparator. Okay, symbolically it looks similar to an op amp, but this is not an op amp, this is a comparator. The way it works is that the inputs are two voltages V 1 and V 2 and the output is a digital output F. The way a comparator works is as follows: if V 1 is greater than V 2, that means plus input is greater than the minus input, then the output will be 1, digital output. If V 1 less than V 2, output is 0. But remember that when the inputs are equal, then the output is not defined. It may be 0 or 1, does not matter, but it is defined when it is greater than or less than. Okay. This is how a comparator works. And priority encoder already you have seen earlier. What is a priority encoder? Let us see how these things can fit in place to create an AD converter. Well, on the left hand side, let us look at the design of a 3-bit. This is a 3-bit AD converter. So, according to what we showed in the previous slide, we have 2 to the power 3 minus 1, 7 minus, then 8 minus 1 is 7. There are 7 comparators. There are n 2 to the power 3, 8 resistances, and we need a priority encoder with 8 input, means actually 1 less, 7 inputs. There will be output will be 3. Now, let us see how this works. The first thing you see that I have a long resistive network starting a voltage, I have a resistive network like this. So, how does it work? So, how many resistances are there? 1, 2, 3, 4, 5, 6, 7, 8. Talk about this point. What will be the voltage here? Ground here, this is R. So, what is the resistance on top? 1, 2, 3, 4, 5, 6, 7, 7 R. So, if you look at this voltage, this is Vref, okay, Vref. This is a resistance divider. So, the voltage here will be R divided by 8 R into Vref. So, the point here will be Vref, I am just writing only V divided by 8. Voltage here, it is 2 R and 6 R on top. This is 2 R and this is 6 R. So, now the voltage will be 2 R divided by 8 R, right. So, it will be 2 V by 8 here, this point. So, what I mean to say is that the voltage at this point will be V reference by 8, voltage at this point will be 2 V by 8, here 3 V by 8, 4 V by 8, 5 V by 8, 6 V by 8 and at this point 7 V by 8. This V is actually Vref, right. Now, what are these comparators doing? Depending on the input voltage, suppose input voltage is less than V reference by 8. So, in the plus inputs, I am connecting the input voltage V in, analog input is connected to the plus inputs of the comparator, and these voltages, reference voltages, are connected to the minus inputs. So, if the plus input is less than all of them, so the output A, B, C, D, E, F, G will be all zeros. So, it will be 0, 0, 0, 0. In such cases, the priority encoder is generating a digital output of 0, 0, 0. That is the lowest voltage level. Suppose now my voltage is greater than V by 8, but less than 2 V by 8. So, only the G comparator G will be 1, all others will be 0, right. You see G is 1, all others are 0, and this is encoded as 0, 0, 1. Now, if it is greater than 2 V by 8, but less than 3 V by 8, then G equal to 1, F will also be 1, but all others are 0. You see? Well, if F is 1, obviously G will be 1, that is why I am showing it as do not care, because it is a priority encoder. If it is greater than 2 V by 8, obviously it is greater than V by 8. Okay. So, in this case it is 0, 1, 0. Similarly, if E is 1, E is 1 means greater than 3 V by 8, then 0, 1, 1. If D is 1, D is 1 means greater than 4 V by 8, 1, 0, 0. Then C means 5 V by 8, 1, 0, 1. Similarly, B is 6 V by 8, 1, 1, 0, and if it is greater than 7 V by 8, A is 1, then 1, 1, 1. And this is priority encoder, means if a particular bit is 1, then the lower priority ones you need not see, you can directly encode it. So, you see, just using a resistive network, I have generated all the reference voltages, and using so many comparators, I am comparing the input voltage parallelly with all these reference voltages, and whatever is the output coming, using a priority encoder, I am encoding it into a digital world. So, see, this conversion is fast because it uses a single process, delay of the comparators plus delay of the priority encoder, that is it. There is no other delay in this conversion, that is why this is very fast. But the problem is that suppose I want to design a 16-bit AD converter. So, you cannot afford to use 65,000 comparators, not possible. Okay. So, this can be used only for very small values of n, right. Let us see more practical kind of converters which you can use for larger values of n. Let us look at something called a counter type AD converter. So, I am showing this schematic diagram on the left. Here again we are using a comparator, but only one comparator, and we are using a binary counter. There is a clock which is coming continuously. Let us see what happens. This counter value is initialized to 0. Suppose it is a 4-bit counter, we initialize to 0, 0, 0, 0, 0, and we are using a DA converter also. We already know how to design a DA converter. So, in this approach we are using a DA converter to design an AD converter. Okay. The idea is very simple. We initialize the counter with 0, we feed it to the input of the DA converter generates a D output which is equivalent to 0, the lowest voltage. You compare this lowest voltage with your input voltage that you want to convert. If you see your input voltage is larger, which means the output will be 1. So, when the clock comes, this will be 1. So, the counter will count, counter will become 1. So, DA converter will increase the output voltage by 1 step, again that voltage will be compared. If V in is still larger, the output of the comparator will be still 1. So, again counter will count by 1 more, 2. So, in this way the counter will go on counting 0, 1, 2, 3, 4, and the output of the DA converter will also go step by step, it will go on increasing, and continuously the comparator will be comparing that increasing voltage with your input voltage. As soon as the D value or the output of the DA converter crosses the input analog voltage, it will stop, because the output will become 0 and this AND gate output will be 0 and the counter will stop counting. So, schematically you can show it like this: the output of the DA converter, it will increase step by step. As soon as it crosses this V in, let us say this is your input voltage level, you have applied whatever voltage you have applied. As soon as it crosses, the counter stops, and at this point whatever is the value in the counter, that is the equivalent digital value in the for the DA converter. This V in, well, instead of calling it D, let us call this as D, this makes more sense. V in will be proportional to D. So, you are getting the value of D, right, 0, 1, 2, 3, 4, but the problem here is that in the worst case for an n bit conversion, the counter will have to count 2 to the power n times, it is an n bit counter. So, number of clock pulses required can be as large as 2 to the power n. So, you can see why I have said that flash type converter was faster, because everything was done in a single step, but here there is a clock, you are applying clock maximum 2 to the power n times. For a 16-bit converter, 2 to the power n can be about 65,000. So, 65,000 cycles may be required to complete the conversion, right. So, whatever we have said, this is actually mentioned here. So, we use a DA converter, a counter and a comparator. Before the conversion starts, the counter is reset to 0. The counter output is fed to the input of the DA converter, and the DA converter output is compared to the input voltage that you are applying. If the input voltage is greater than the DAC output, then the counter increments by 1. If it is less, then the counter does not increment anymore and conversion is complete. As I had said, the worst case conversion can be 2 to the power n time, number of clock pulses. Now, let us modify the design a little bit. We move to a method which is called tracking type AD converter. Let us see. For a simple counting type AD converter, what we are doing? We are having a counter starting from 0, we are counting up and we are stopping as soon as we cross the level of the input voltage. That count value will be my digital output. Now, suppose what I do, instead of a binary counter, normal up counter, we use a up down counter. Now, here we say that we want to continuously track the input voltage. We do not want to start counting from 0 every time. One problem with the counting type converter was that you always start counting from 0, 0, 1, 2, 3, 4. Suppose your input voltage is equivalent to a count of 1000. So, you will have to count 1000 times, 1000 clock pulse. Next data you sample, maybe it was 1005, again from 0 you will have to count 1005. Next sample value was let us say 1001, again from 0 you have to count to 1001. So, it was very time consuming. So, what I is saying is that suppose the input waveform is slowly changing, we know that from 1000 it can go up to 1005 or let us say 995, not much change. So, why every time start from 0? If you remember the last count value, why do not you start from there, either go up or go down? So, you use a up down counter instead of a normal up counter. So, your modified schematic will look like this. You use an up down counter and rest is very similar. From the output of the DA converter, you use the comparator and the comparator output can be either 0 or 1, and similarly the output of this clocked will be 0 or 1. So, when it will be 0? It will be 0 if V in is smaller, okay? The DAC output is larger. So, if DAC output is larger, I will have to reduce the value of the DAC output. So, 0 means I will be counting down, I will have to reduce the value of DAC. But if it is 1, which means V in is larger, DAC output is smaller, I have to increase the DAC value. So, if it is 1, I have to count up. So, there is no concept of stopping the count, I am continuously doing it. If it is 0, the count is counting down, if it is 1, it is counting up. This is called tracking type because the DAC output tries to track the variation of the input waveform continuously. So, as this example shows, suppose this is my input voltage, this straight line, just an example. Suppose the input voltage is changing linearly in a straight line, and the first time you start with 0, 0, 1, 2, 3, 4, 5, here you cross. So, here you have one conversion. After that, if you go up, you see that your input voltage is less than that, that is why you decrease, here is a down count. Okay. Next step, it is higher, you increase. So, again it is crossed, next step you decrease, next step your input voltage has increased. So, it will be increasing, here it crosses, again it decreases, again it increases 2 steps. So, it is continuously trying to track. So, it is not coming to 0 and from 0 it is again trying to search, right. So, this tracking type of AD converter works much faster as compared to a simple counter type. Counter type, for those of you who know programming, it is like a linear search. You are searching for a certain value of V n starting from 0, 0, 1, 2, 3, 4, 5, 6, you are going up. Now, in tracking type it says once you have found it, for the next time you start from there, either go up or go down. Tracking type works well for signals which are changing relatively slowly, okay, because it changes very fast. So, it may not be able to track. So, whatever we have said is here. Here we use a binary up down counter. If the comparator output is 1, we increment the counter. If it is 0, we decrement the counter. As I said, this is suitable for relatively slowly varying waveforms, because the reason is that if V in changes too fast, the counter may not be able to track the changes, because we are basically using a clock to either count up by 1 or count down by 1. If it changes in a jump by 100 steps, again you will have to count up 100 steps slowly, it will not be so efficient, right. But in the worst case, the conversion time is still 2 to the power n, right. So, we come to the end of this lecture. In the next lecture, we shall be looking at a similar kind of a technique, but a scheme which works much better in the worst case, because here also is said in the worst case I may have to start from 0 and go up to maximum 2 to the power n. But in the next method that we shall be talking about in the next lecture, we will see that for an n bit conversion, maximum n clock cycles will be required for one conversion. Suppose I have a 16 bit converter, I do not need 65,000 2 to the power 16 cycles, clock cycles. I need maximum only 16 clock cycles. It will be much faster and scalable. For larger values of n, you will be able to use it. This will be discussing in the next lecture. Thank you.